Okay, guys, we're now going to prove the location of the shear center using very basic principles on mechanics. No, so I cannot give you the a more detailed derivation on the shear center determination. So this is the simplest that I can explain it to you. Okay. So as I've said a while ago in my previous video, the shear flow for a certain shape, uh, whether it's a semi-monocoque or, by the way, a monocoque shape is something like a shell or a part of a shell, no? So imagine you have a material that serves to be the walls of a car or an aircraft or a shed. So it just represents the surface of the material, wherein the thickness is actually small compared to the whole surface. No, so we can now consider a plate element, a shell, a part of a shell, and so the shear center concepts and the shear flow concepts are very much applicable to it. Okay, so if I have a shear force applied, let's say at the center of gravity here, my legs will experience what you call shear stresses. And again, those shear stresses, which are basically computed on the basis of the formula VQ over IT, may be converted to a shear flow, which is Q equals VQ over I. Okay. Okay, so we just removed the T here, meaning to say I just multiplied my shear. Okay, sometimes shear is represented by V or FV. Sometimes it can be represented by tau. Okay, the Greek letter tau. Okay, so this Q here will now flow uh, as directed, starting from a surface. It will start 0 here, and then it will actually increase in magnitude as it approaches the neutral axis. So remember that this neutral axis here is one reference point to which your maximum shear stresses or shear flow will occur, but not all the time. There are special cases. Okay, so there are special cases, but mostly your shear flow values will start from 0 and then increasing up to this point. And then again, at this point, it suddenly decreases a little bit until it flows to the right, and then it reaches a very small value here, 0. Okay, in short class, we can convert this Q into F1, F2, and F3, no? By simply taking the average of the shear flow values from 0 to a maximum. Okay, so if I'm going to graph now my shear stresses, okay, let me graph it here so as not to para hindi tayo malito. Okay, so my graph for the shear stresses now will start from 0 here, and then it will increase up to this point, where in the neutral axis or the centroid is actually directly projected there, and then it will decrease a little bit here, okay? And then of course here it will have a value the same as that, and then it will simply decrease there. Okay, this is more of a straight line. So don't worry about how to determine when it is a curved line or a straight line. Okay, so uh, practice will actually give you the confidence on when and when not to assume it to be a curve or a straight line. So in short class, we're just taking the average. We're just taking the average of this in order to get F1, okay, and take the average of this in order to get F2, okay, and the F3 also, we can take the average of this in order to get F3. But we will be concentrating more on the F1 and F2 since later on, if we will try to look at the system of forces, we can actually locate a point O here, in which if we take the summation of moment, this will just cancel out. Okay, so that's the good thing about manual computations. You can do it classically by just observing the situation, and then if we can get a point that will eliminate all the other forces in taking the moment using the Varignon's concept, then everything will be simpler. Okay, so our target now is to simply get F1 and F2 and get the moment here. Okay, so or take the summation of the moment here at point O. So that will be our objective. Okay, so taking now the summation of moment equals 0 at point O, then we have Vx or V times Ex is equal to simply F1, okay, F1 and F2, you just add them multiplied by X bar minus what? Thickness. Okay, and actually this is the formula for our XO a while ago. Tama? Diba ito yung XO natin kanina? So, which means to say that if F1 and F2 is equal to V by way of trying to get the summation of forces vertical, then the solution is very, very simple. No? We don't have to worry about it. We just cancel V here. This is now your V value. Okay, and then this will now cancel, and we have your Ex is simply equal to XO, which is exactly the formula we are looking for. So this is exactly at the intersection of the mid-center lines or the midlines of the legs of the angle. And due to symmetry for equal angles or unequal angles or all angles in general, okay, all L-shape or angular shape sections, your EY will simply be equal to okay, sorry, this is not pertaining to that. It pertains to this. Okay, so all angles section, your Ex will simply get this formula, and for equal angles, your EY will simply be equivalent to Ex. Okay, to proceed with the computation, the last requirement is the computation of the location of the maximum stress at the neutral axis. We have to assume a value of V, or else we cannot solve the problem, and define some area that will make us compute your forces F1, F2, and F3 if we want to compute it. No? So we define now an area. Okay, let's draw now the area concerned here. So we have here the first area, and we have again a small area here, and then we have the last area here. Okay, so where's this area? Why is this area cut into three? No, so we know for a fact. Let's make another color. Okay, so we know for a fact that your F1 and F2 and F3 are divided in such a manner that it separates the vertical element into two. No, so this is now your F1. So your F1 will actually be giving you your area 1, and this is your area 2, and of course this is your area 3. But area 3 is not actually very important. Now for the Q1, what is a Q? A Q is actually a first moment of area, no? Defined in your strength of materials, which is simply a YDA, okay, area times a moment arm, or simply in geometrical sense, it's simply an area times y bar. Okay, so it's just an area y bar, and this area has a y bar equivalent to the centroid of this up to this point here. Okay, so this is my y1, and if I want to find my a1 and q1, so I simply multiply now my area 1 with respect to y1, and this is my y1. Okay, so y1 is simply your total length here, L2, minus y bar, okay, divided by 2. Okay, so I get this. So where will I use this? I will use this later on my formula VQ over I. T, okay, or my shear flow formula, which is VQ over I. So I is the IX because we are looking into this axis as your axis of rotation. Okay, so these are the IX here. And we have solved this a while ago. No? So we will be using the value of IX from the computation a while ago. And so is true with your A2. We have to define an A2 and a Q2 in order to get the shear stress and the shear flow values, which is actually computed here on the last slide I have. So tau 1, okay, so assuming V is equal to 100, so I multiplied it by 1 times 10 to the 3 in order to get a Newton value, okay, because this is in kilonewton. And then I solve for tau 1, VQ1 over IXT. Okay, I got this value. Automatically, this will be in megapascal because I have a Newton millimeter cube divided by millimeter to the 4th times millimeter. It will be in Newton per millimeter square, or simply megapascal. So if you have formulated all the given values, it's very easy to come up with computation, especially if we are using computers, no? Kung wala kang computer, you have to compute it using calculators, of course. Then Q1 is simply tau 1 multiplied by T, so you get here a value, and taking the average. Okay, so remember what I told you a while ago, that the force F1 here is simply equivalent to the average. Let's say we start from 0 up to 2.338 kilonewton. We just take the average, no? 0 plus Q1 divided by 2. So that's the one that was plugged in there. Okay? Q1 divided by 2. Okay, of course, this is a force that is a force per linear millimeter. You have to multiply this by what? The length of this. If this is your plate, what is the length of this? So the length is simply L2 minus Y bar. So this is what is uh, given on your geometry figure on the other slide. Okay, so I now computed my F1, and similarly, defining A2 and Q2 will give me my tau 2 and Q2 and F2. Okay, so uulitin mo lang yon. But this time, your average will be equivalent to your Q1 plus Q2 because you are starting with a value. Let's say this is now my element. Okay, I have a Q1 here, and then I have a Q2 here, and the length of this is simply my Y bar. I cannot write a Y bar, no, in MathCAD, so I just make use of the word bar there, but it's the same as Y bar here. Okay, so Q1 plus Q2 on the average divided by 2 times Y bar becomes 2118 or 21.18 kilonewton. And if I add the two, you will notice that class, the final value of F1 plus F2 will not match your shear. So there's a very, very big error using only average values. No? So that's why, again, this is just to show you how it works, but this is not a good procedure on dealing with the shear forces because you are just taking the average of the shear flow at a very extreme values. But there's a much more, a better procedure, and that is of course by using integration or calculus. So if I make use of an integral formula, so this is just my formula, no? Okay, so I just get V, this is now my Q. Okay, my Q now is an integral expression. I'm now integrating from 0 to L2 minus Y bar plus negative Y bar to 0. Okay, so these are my two elements, and of course this is divided on the neutral axis. The first represents my F1 there, the second represents my F2. Okay, so if you want to make use, this is now my F1. Sorry, this is my Q1 rather, this is my Q2, okay, which will represent F1 and F2. So I now have what? The integral from, I integrated here as 0 as my neutral axis up to a value of L2 minus Y bar. And then I integrated from a negative value of Y bar here, and then a maximum value of 0 there. And then divided by Ix, which is constant, I get a value for my Q. This is now no longer an average, okay? So not an average value. And this is very, very almost accurate. Of course, meron lang still a discrepancy because we just rounded up the other values a while ago in the computation. But it matches now my total F, which is equivalent to F1, F2, very near to your V. Okay, so this is 109 against 100. Okay, so the reason for some errors here are because you only assume that shear acts at the center. Okay, eventually when you go into into the corners. How do you manage to uh, consider? Okay, so if you are only considering the midlines here, you cannot capture the effect of the values of your shear on this transition, on this junction. Okay, so that's why there's a slight error of 9 kilonewton, but fairly well compares well with the shear here, rather than using simply the average values of Q in this method. Okay, so don't worry, class. This is just to give you additional information on how shear flow works, for you to be able to understand what shear center is all about. But in your computation for the lateral torsional buckling, you don't need to compute for F1, F2, etc. You just need to remember how the shear flow concepts works in very basic angle shapes, steel shapes. And of course, you have to know how to compute for the shear center. Okay, and the computation for shear center is done using the principle I just gave you here. Okay, so summation moment at a certain point is equal to 0. So now question, can you take moments anywhere you want? Of course, you can take anywhere, but you are probably making it difficult if you cannot eliminate maybe one or two forces just to simplify your equation. It's just like taking moments on a beam. If you know where to take the moments, then your work will be easier rather than difficult. Okay, so I will just entertain your questions if you have some questions on this. I will stop my lecture on shear flow and shear center to this point. Thank you very much.